Okay, let's look at this example. We want to evaluate the triple integral over the square root of 3x squared plus 3z squared dv, where q is the solid bounded by y equals 2x squared plus 2z squared and the plane y equals 8. So the first thing we want to do is give a rough sketch of my region of integration q. Okay, so y equals 2x squared plus 2z squared is a paraboloid that opens up around the y-axis. And I said rough sketch, so I'm just giving a rough sketch here. And the plane y equals 8 is the plane that's parallel to the xz plane at y equals 8. And so that's going to hit my paraboloid here at y equals 8. So I have something that looks like this. Okay, so here's my q, and I want to think about the bounds on my variables. Well, here it's natural to take my sort of 3D slices going this way now. And so my y values are going to start back here along the paraboloid and go to y equals 8. So I'm looking at bounds on y of 2x squared plus 2z squared less than or equal to y less than or equal to 8. All right, now my region for the other two integrals, I want to think about taking this surface here and projecting it down onto the yz plane. Now when I do that, you can see that this circle here is what's going to get projected down. This is what I get when I set these two equations equal. So 2x squared, whoops, start with x, 2x squared plus 2z squared equals 8. That says that x squared plus z squared equals 4. That's a circle in the xz plane of radius 2. So let's mark that as 2, 2, negative 2, negative 2. So my bounds on x and z, well, let's do z first. I'm going to take vertically simple region. So my z slices here are going to go from the bottom half of the circle to the top half of the circle. So that goes from negative square root of 4 minus x squared to positive square root of 4 minus x squared. And x here, as I take my slices, is going to range from negative 2 over to 2. Okay, so my integral is the integral, let's do square root of 3x squared plus 3z squared, and I did dy, then dz, then dx. So the bounds on y were 2x squared plus 2z squared to 8. The bounds on z were negative, square root of 4 minus x squared to positive square root of 4 minus x squared, and then the bounds on x were negative 2 to 2. Okay, so if I integrate this first with respect to y, I get the integral from negative 2 to 2 of the integral from negative square root of 4 minus x squared to square root of 4 minus x squared. Notice there's no y here in my integrand, so this is treated like a constant, so I just get y times square root of 3x squared plus 3z squared, evaluated from y equals 2x squared plus 2z squared to 8 dz dx. So that's the integral from negative 2 to 2 of the integral from negative 4 minus x squared to, sorry, square root of that, to square root of 4 minus x squared of 8 square root of 3x squared plus 3z squared minus quantity 2x squared plus 2z squared times the square root of 3z squared plus 3x squared. I've switched my x and z. Here, let's 3x squared plus 3z squared. All of that is dz dx. Now, take a breath. What a mess, right? This is going to be really hard to integrate. So what I want to do is notice, what if I just erase this and call it dA here? And I'm going to erase my bounds and call this the integral over, double integral over R, where up here, let's see if I can fit it on my screen, up here is my R, right? It's this circle of radius 2. Now what did we do in the last section? We set up double integrals with regions of integration like circles using polar coordinates. And so we can do that here to make our life a little bit simpler. So if I switch to polar coordinates here, what are my bounds on r and theta? Well, r is a circle of radius 2, so r goes from 0 to 2. And theta goes from 0 to 2 pi. All right, and this works out nicely for me because here I'm in the xz axis. So here we have x squared plus z squared equals r squared. And so when I look at my integral down here, I have a 3x squared plus 3z squared I can replace with a 3r squared. Here I can replace with a 2r squared, and again a 3r squared there. All right, so let's do that replacing. So this becomes, let me write what we're doing, convert to polar. All right, so what does this become? It's the integral from 0 to 2 pi of the integral from 0 to 2 of 8 square root of 3r squared minus 2r squared square root of 3r squared. And what happens to my dA? I have r dr d theta. Okay, so what do we get? I get 0 to 2 pi of the integral from 0 to 2. If I distribute and clean things up, I'm going to pull a square root of 3 out, and so I'm left with an 8r squared once I distribute this r in. So 8r squared minus 2r to the 4th dr d theta. And now this isn't so terrible to integrate, right? So I've got the integral from 0 to 2 pi of root 3 times 8r cubed over 3 minus 2r to the 5th over 5, evaluated from 0 to 2, d theta. Oh, I'm not going to fit it. Let's copy this and move to the next page. So that's the integral from 0 to 2 pi of root 3 times, I'm going to have an 8 times 8 or 64 thirds minus 2 times 2 to the 5th, so 64 fifths d theta. That's the integral from 0 to 2 pi of root 3 times 128 over 15 d theta. And that's going to integrate to give me 256 root 3 times pi over 15. All right, so don't forget to take advantage of converting to polar coordinates if it's useful.